right, hello everyone. So I'd like to start a series of lectures or discussions about the super important concept of momentum. Okay, so in the last set of lectures we talked about energy, and we started off by saying, yes, energy is of central importance to physics, and that's true. Well, it turns out that momentum is also equally important and central to how physics works, okay, how nature works. Okay, and the reason has to do with what momentum actually is. Okay, so now all of you in high school physics, you know momentum, at least in a Newtonian universe, is defined as mass times velocity. And so, and that's a useful definition because, as we'll talk about, that quantity, that mass-weighted velocity, is a conserved quantity. Like energy and momentum is also conserved. Okay, so that's why it's an important thing to define. Okay, but these first-year textbooks, introductory physics textbooks, they won't ever tell you what momentum actually is. And that's because, just like energy, to understand really anything meaningful about energy, you need to understand a little bit about special relativity, namely E equals mc squared. Similarly, to understand anything really meaningful about momentum, anything deep about momentum, you need to understand a little bit about special relativity as well. And so the short answer is that momentum, what is it? It's a measure of the rate of flow of energy. So let me give you an example. So we've got a baseball, and that baseball is in motion. And we say, yes, its momentum is mass times velocity. Great. But what actually is that? What does that represent? What's the meaning of that? Well, if you think about a baseball, so a baseball has a tremendous amount of rest mass energy. So let's say 1 kilogram equals mc squared. So 1 kilogram, say, times 10 to the 7 c squared is about 10 to the 17 joules. So that baseball has about 10 to the 17 joules of rest mass energy. When that baseball moves from here to here, a tremendous amount of energy has moved from here to here. There's been a flow of energy. Okay, and so you might ask, well, what is the rate of flow? How rapidly is that energy flowing? Well, that depends upon how fast the baseball is moving. If the baseball moves slowly from here to here, there's a certain rate of energy flow. Okay, but if the baseball is moving more quickly, then the rate of energy flow, the rate at which energy moves from here to here, is larger. Okay, and so larger momentum, larger mass times velocity, is exactly the same thing as larger rate of energy flow. Okay, but you can't make that connection to the real meaning of momentum without understanding that all the objects around us, cars driving around, wind blowing, those represent tremendous flows of energy from place to place. Okay, so tremendous rates of flow of energy from place to place. And so the momentum, what it is the measure of that rate of flow. So basically the momentum times c squared, a really big number, will give you the rate, will be something that measures the rate of energy flow. Okay, and so we'll talk about that. That's super interesting and super deep and important. We'll mention that a little bit more towards the end of these lectures. Okay, but sort of at face value, this idea of momentum, mass times velocity, why it is such an important concept is because just like energy, momentum is a strictly conserved quantity. So momentum is conserved. Okay, so that is a very deep and profound principle. So there has never been an experiment that we have ever conducted, okay, even at the LHC, super ultra-relativistic particles and so on, we have never seen a single violation of this principle of conservation of momentum. Okay, so to give you sort of a feeling for this, to sort of make things a bit more concrete, let's sort of proceed in the same way that we did with energy. Energy is also a strictly conserved quantity. So we can draw an exactly parallel discussion. So what we imagine is a region of space over here. And we will suppose that this system is isolated. Okay, so when we say the system is isolated from, as far as energy conservation, we mean no energy in or out. When we say it's isolated from the point of view of momentum conservation, we say that there is no momentum in or out. So for example, if you had a baseball moving like this outside, well, there's momentum outside, and then it flows through the boundary, and now we have momentum inside. Momentum has been transferred from outside to inside. So we're not allowing that. We're saying there's no momentum flowing in or out of that system. So isolated system means no momentum, and momentum is the letter P with a vector on top, because momentum is a vector quantity. Okay, it's like Newtonian physics, it's mass times velocity. So no momentum transfer in or out of the system. Then that system is isolated. Okay, and then so let's imagine, as we did before for the case of energy, we will divide that system into two parts, two subsystems, 1 and 2, and we will imagine that, say, at some instant of time, this subsystem number 1 contains some momentum P1. Okay, so just like there are lots of mechanisms by which nature can store energy, there are also lots of ways in which nature can store momentum. The simplest way is a massive object in motion, and its momentum is, at least in Newtonian physics, mass times velocity. Okay, and you're familiar with that one. But also momentum can be stored in fields. It's very important. Fields are real. So electromagnetic field, for instance, light, a light wave. So a light wave going like this, that light wave has momentum. Okay, so if you put a mirror up here, that light wave will reflect off the mirror, exert a force on the mirror, and knock it over if the light is intense enough. Okay, so light carries energy as well as momentum. Okay, so fields can carry momentum, and that's super important. Okay, just like massive objects moving around carry momentum, fields can carry momentum. Anyway, so we have in subsystem number 1, at some instant of time, we have stuff in there which altogether represents a certain amount of momentum. Okay, so let's suppose that momentum is a vector quantity. And so suppose it looks like this. This is the momentum in system number 1, say initially. Okay, and similarly, at that same time, there's a momentum, an amount of momentum P2 stored in subsystem number 2. Okay, so P1 or P2, so that represents the momentum stored. Momentum stored in systems 1 or 2. And there's the same sort of thing with energy. There are various ways of storing energy. There are various ways of storing momentum. There are various ways of transferring energy from place to place, or one form to another. There are also various ways of transferring momentum. Okay, so we'll be talking about storage of momentum and transfer of momentum. Okay, so and then the idea is this. Suppose that the momentum in this system changes by a certain amount. Okay, so we'll suppose that P1 changes by, let's call it a vector I, and put a minus sign in front of it. So P1 changes by minus I. Okay, so that means that you start with P1 and you add to that vector negative I. Okay, let's just suppose this is negative I. Okay, that means P1 changes from P1 to P1 plus negative I. And so maybe this is P1 initial, then this would be P1 final. Okay, so P1 changes by minus I means it changes from this vector to that vector, and the change is the vector minus I. Okay, if P1 changes by minus I, then P2 must change by plus I. Okay, and so suppose that P2 was initially this vector. Remember, P is a vector quantity, so it's a quantity of some length and some magnitude. So if this is the initial momentum in system number 2, and if P1 changed by minus I, then P2 must change by plus I. So P2 changes from P2 to P2 plus I. If this is minus I, then this is plus I. And so then P2 changes from P2 to P2 plus I, adding those vectors tip to tail. This is then P2 final. Okay, so that's the idea. So we say that there has been a transfer of momentum in the amount of I from system 1 to system 2. So system 2 has changed by, the momentum has changed by plus I when I moved from there to there, and system 1 changed by negative I. Okay, so in the end we get the change in the momentum in system 1, delta P1, so P1 final minus P1 initial, that's equal to minus I. Okay? So it went down by I, so to speak, but because I is a vector, it's not really going down, it's just changing by minus I. So then that implies that the change in the momentum in system number 2 has to be the opposite vector, plus I, okay, such that the change in the total momentum, which is the change in P1 plus the change in P2, which is minus I plus I, is 0. Okay, so when we think about momentum conservation in terms of various ways in which momentum can be stored, we say, yes, the momentum in this one changed by minus I, so the momentum in this one changed by plus I, without any thought for how the momentum is transferred from location to location, from one side to the other side. Then we're thinking in terms of, then we would write the principle of conservation of momentum in the form delta P total for an isolated system is equal to 0. Okay, so whatever change in momentum happens in this system, there's an opposite change in momentum in that system, so that the total momentum in the isolated system remains constant. Okay, great. So let's do sort of a quintessential example, which is basically in particle physics. So the idea is, the picture in your mind is something like we have two charged particles, positively charged particles, that repel each other, and they start, say, moving like this through space. And when they're far apart, they feel very little repulsive force, but as they approach each other, they feel repulsive forces. And so they will move like this. They will repel each other and then fly off again. Okay, so they're moving on basically straight lines as they come in, then the lines get curved like this, and then when they get far apart again, they basically move on straight lines. That's the essence of any particle physics experiment. It's also the essence of billiard balls coming together. So here's two billiard balls coming together like this. They interact, okay? They touch each other, and they exert forces on each other. The two balls compress slightly, and like little springs, they try to re-expand, and so they exert forces on each other, equal and opposite forces. Newton's third law, equal and opposite forces, and then they repel. They come together and then they repel each other. Okay, and so that's the quintessential example of momentum conservation, or momentum being transferred from one system to another. Okay, so the picture that we draw is something like this. Let me see if I can fit this on here. Yeah, okay, so so what we imagine is a picture that looks something like this. We have a particle coming in and going out like this, and we have another particle coming in and going out like this. So here's the particles coming in, and maybe electrostatically they repel each other like this, and then they fly out like that. And so we will call this particle subsystem number 1. It's the one that lives in this half of the universe, in this half of our isolated system. And we'll call this subsystem number 2, this particle number 2 here. And then the idea is we are in some inertial reference frame. So as usual, all of our discussion takes place in some inertial reference frame. It doesn't have to. We can be in an accelerated reference frame, but then we need to think a little bit more carefully. Okay? So what we have is, say, at one instant of time, particle number 1 is sitting over here, and it has a mass m1. And particle number 2 at this instant of time, say, is over here, and it has a mass m2. Okay? And these particles are in motion. So at this simultaneous time, at this instant of time, we have, say, particle number 1 has some velocity, say, v1, at that instant of time t, and particle number 2 has some velocity v2 at that same instant of time. Okay, so they're doing that. And then the idea is we're going to imagine that these particles are exerting forces on each other. And so this could be anything from two billiard balls coming in like this, and when they touch each other, they exert a contact force. Or it could be these particles are electrically charged, and they exert a force through the electric field. Or they are gravitationally charged, and so when they fly by each other, they do something like this, and so on. Okay, so there's some interaction. So at this particular instant of time, there is a force. In this case, we're imagining electrostatic repulsion. So there's a force that particle 2 exerts on particle 1 at this instant of time. So we'll call this the force on particle 1 due to particle number 2 at the instant of time t. And of course, it's a vector. And then the idea is that we're going to assume and this isn't always true, but we're going to assume that the force of interaction satisfies Newton's third law. Okay, so the force on 1 due to 2 at this instant of time is equal in magnitude but opposite in direction to the force on particle number 2 due to particle number 1 at that same instant of time. Okay, so that's our basic picture. This is a very, very general sort of picture of things in nature interacting with each other through some forces. Okay, and the only thing that we are assuming here, and this is an important assumption, Newton's third law is at the heart of momentum conservation. Actually, that's saying it too strongly, because we'll see a little bit later that that Newton's third law does not always apply. Okay, and so then what you have to do is include not only the particle momentum, you know, the momentum of objects in motion, but you also have to include the field momentum, the momentum of, say, the electromagnetic field. And when you include particle momentum, you know, mass times velocity type momentum plus field momentum, then that total momentum is strictly conserved. Okay, but anyways, so we are assuming Newton's third law. So we are assuming that 0 is equal to F12 at that instant of time plus F21 at that instant of time. So this is the third, we're assuming the third law. And I'm putting law in quotation marks because it is not always true. Okay? So momentum conservation is always true, but Newton's third law is not always true. Okay, so, but for the purposes of this course, this is good enough. Okay, so then we say, yes, but what is F12? We know that forces acting on an object are going to cause an acceleration in proportion to the mass, or inversely proportional to the mass. So for a given force with a small mass, there'll be a large acceleration. For that same given force for a large mass, there will be a smaller acceleration. So by the definition of inertial mass, resistance to changes in motion, we know that the force that's acting on particle number 1 due to particle number 2 causes an acceleration of particle number 1. So it's an acceleration of particle number 1 at the instant of time, weighted by the mass. So it's m1 times the acceleration. Dropping my little cap here. Okay, and similarly, the force that acts on particle number 2 due to particle number 1 at that instant of time causes particle number 2 to accelerate with an acceleration a2. Okay, and so we have a mass-weighted acceleration, mass 2 times the acceleration of particle number 2 at that instant of time. Okay, and so this is basically follows from the definition of inertial mass. So you apply a force to an object and you measure you measure its rate of acceleration, rate of velocity change, and so then the ratio of those two gives the mass. Okay, so if you apply a given force, small acceleration is large mass, large acceleration is small mass. So this is really the definition of inertia. So this follows from inertia, the definition of inertial mass. Okay, and then you say, okay, but we also know from kinematics, what is acceleration? Well, that's the rate at which velocity is changing. So we have m1, acceleration a1 is the time rate of change of velocity, v1. So v1 is first this, then this, then this, then this, then this. So the velocity is clearly changing. And in this direction, there's certainly a component of change in that direction. In the direction, in fact, that is the change in the direction, is the direction of the force F12. And similarly, we have plus m2 times the time rate of change of velocity 2. And that's acceleration a2. So this is just kinematics. Okay, and then we say, let's suppose, just for simplicity, keep things as simple as possible for now, we will suppose that these two masses are constant. They're not changing. Now, that's not the only thing we'll consider. So we will consider changing masses when we consider how rockets work and so on. But for now, we'll assume that these two masses, m1 and m2, are constant. Okay, which means that we can take the time derivative, we can take the mass m1 inside the time derivative. So mass times time derivative velocity is the same as the time derivative of the mass times the velocity. So we can pull the time derivative outside of the whole thing. So this is d by dt of m1 v1 of t plus m2 v2 t. Okay, so this is assuming that m1 and m2 are constant. Okay, So then we find a very interesting and powerful result. We find that the time derivative of this thing is equal to 0, which means that this thing is a constant. And this thing is a vector. It's vector v1 times a scalar m1 plus vector v2 times a scalar m2. This whole thing is a vector, and it's constant. Okay? It doesn't change with time. And that's remarkable, okay? Because if you look at this picture, you can clearly see that v1 is changing like crazy. It's a very complicated function of time. Okay? v2 similarly is changing all the time. So v1 and v2 are complicated things that change in a complicated way under time. And yet the sum of the mass-weighted velocities remains constant in this interaction, regardless of what this interaction is, whether it's contact forces, whether it's electrostatic, whether it's gravitational, or whatever. It doesn't matter what the interaction is. It is always true as long as this is satisfied, as long as that's the nature of the interaction, Newton's third law. Then it will be true that this sum of mass-weighted velocities remains constant through an interaction, which is really remarkable. So if you think about, say, the LHC, okay, so we've got particles, say 2 protons coming in, relativistic protons coming in. So there is some, mass times velocity of particle 1, mass times velocity of particle 2. They come in like this, and then they interact in some super complicated way involving, fundamental forces, elementary forces, and so on. And what comes out is not 2 protons, but a spray of all kinds of different particles, electrons and, mesons and all kinds of particles spray out, photons spray out of this thing. Okay, yet the total momentum going in, the sum of mass-weighted velocities of the particles going in is always equal to the sum of mass-weighted velocities of the particles coming out. That's a very powerful principle, regardless of what the interaction is. Okay, so that's very, very powerful. So individually, v1 and v2 can be complicated functions of time, but this sum of mass-weighted, how should I say this? So these guys, v1 and v2, change in complicated ways, but the sum of mass weighted, by mass weighted I mean you're multiplying the quantity by the mass, by the sum of the mass weighted velocities is equal to a constant. Okay, it never changes. Whatever it was initially, at some initial instant of time, you calculate that sum of mass-weighted velocities, it will always be equal to the sum of mass-weighted velocities after the interaction. Okay, so velocities themselves are not very important in physics. What's important in physics, what the special quantity, is a mass-weighted velocity. There's something special about that. So let me see. Well, I have enough room to do this. So yeah, let me just sort of fit it down here. I'll just get rid of a little bit of this diagram over here. Okay, because I want to have some room to do something else over there. Okay, so what we do is we define. There's something special about a mass-weighted velocity, so we give it a special symbol, p. And it's a vector. So p is equal to the mass of an object times its velocity. Okay, and that thing is called the momentum. Okay, so, so that's the momentum. Okay, and it is actually also let's write it sort of a couple different ways. Mass-weighted velocity and this is also, interestingly enough, if you look at Newton's Principia, he didn't use velocities a lot. What he used was what he called the quantity of motion. And he never used the word momentum, but that's really what it is. Okay, so in his language, the mass times the velocity is Newton's quantity of motion. Quantity of motion. Okay, so the idea is something like this. In nature, Nature doesn't really care about the velocity of an object, how fast it's moving, or its mass. What nature really cares about is the quantity of motion, the amount of motion that's happening, and that is this mass-weighted velocity. So for example, you could have a large object, large mass moving slowly. That will have a certain quantity of motion, a certain oomph of motion. But you can also have a small mass moving very fast. Okay, so these two totally different, seemingly totally different situations have the same quantity of motion. And that's really what counts in a lot of physics. So when you study quantum mechanics, for instance, you will never talk about the velocity of a particle. You will only ever talk about the momentum of a particle. So if you think a little bit in quantum mechanics, what is one of the basic sort of notions in quantum mechanics? Well, the Heisenberg uncertainty principle. Delta x, delta p is greater than or equal to h bar divided by 2. So it's p that appears here, not mass times velocity. Okay, so momentum is more fundamental in physics than velocity. And similarly, when you go on to do more advanced classical mechanics, again, you won't be talking a lot about velocities. You'll be talking much more about momenta. So one thing I want you to get used to immediately is we have kinetic energy defined as 1/2 mv squared. Well, if we use the idea that P is m times v, then kinetic energy can also be written as E is equal to, kinetic energy is P squared divided by 2m. Okay, so that's an important thing to get into your head instantly. Okay, so kinetic energy, we can write it as 1/2 mv squared, but more basically, it's written as P squared divided by 2m. Okay, that's the same thing as 1/2 mv squared. These are two equivalent expressions for kinetic energy. And so you should get used to using this expression, P squared divided by 2m, and immediately recognize that as the Newtonian kinetic energy. Okay, so yeah, that's about it. Okay, so now what I want to do is I want to flesh out this idea of momentum conservation. And again, there are sort of two ways to think about, just like we had conservation of energy, there's two ways to think about it. So we had energy can be stored in some situation. Energy can be stored in different ways in different locations. If energy goes down over here, it can go up over here. It must go up over here. So the total energy of the isolated system remains constant without thinking about how the energy got from there to there or from one form to another. Okay, that's the storage way of thinking about conservation of energy. Delta E total equals 0. We can do the same thing with momentum. Okay, we can think about momentum storage and then just say, well, delta P total is equal to 0. Or we can think about conservation of momentum from the point of view of transfer. So here's subsystem 1, subsystem 2. There is a transfer of momentum from 1 to 2. So the momentum of subsystem 1 changed by a certain amount. There was momentum that got transferred to subsystem 2. Okay, and so subsystem 2 will change by the opposite amount. Okay, so we can think about momentum conservation from both of those ways, storage and transfer. Okay, so this definition, I just want to sort of reiterate here, this definition that P is equal to mv, why do we define that? We define it, for one thing, because it is a useful definition. This mass-weighted velocity is the thing that is conserved. It is a strictly conserved quantity, just like energy is a strictly conserved quantity. Okay, so let's look at this momentum conservation from the point of view of momentum storage. And the simplest way to store momentum is in a massive object that's in motion, mass times velocity. Okay, so for an isolated system, if you have an isolated system of, say, a whole bunch of like rocks floating out in space, moving around, and it's isolated from the rest of the universe, they can be hitting each other or exerting forces of various kinds on each other, then for an isolated system, we know that P total, the total momentum, at any instant of time in that system will be the sum of the mass-weighted velocities. Okay, so it'll be equal to the momentum, mass times velocity of particle number 1 at some instant of time, plus the mass-weighted velocity for particle number 2, so P2 at that instant of time, mass 2 times velocity 2 and so on, plus dot, dot, dot for however many like objects you have moving around and interacting with each other, say in some big complicated solar system or whatever. Turns out that P1, P2, and P3 and so on, they may be changing in very, very complicated ways, but it will always be true that no matter what the interaction forces are, as long as they satisfy Newton's third law, it will always be true that the total momentum remains unchanged. The total momentum is always the same constant value. Whatever value, whatever total momentum, whatever total quantity of motion that you had to begin with, that will always be in that system. It can never change. So another way to write this is that 0 is equal to the change in the total momentum. Okay, so this way of expressing it. Okay, so remember that delta means change in. So P total final, this means P total comma final minus P total comma initial. Okay, so just take the final total momentum, so add up take the sum of the mass-weighted velocities after the interaction. That's going to equal the sum of the mass-weighted velocities before the interaction, regardless of what that interaction is. Okay, so we have that. That's one way of thinking in terms of energy storage. So let's just draw this, this picture here. So I'll redraw this picture over here, and I'll label it a little bit differently. So let's see. So let me leave some room for the other stuff down there. So we've got this particle comes in like this. That's particle number 1 that we drew before. And this is particle number 2. Just like this. And let's suppose that particle number 1 is light and fast. Okay, so mass m1 is relatively small, but it's moving fast. So it's got some initial velocity v1 initial. Okay, so there's some oomph of motion, some quantity of motion in that direction stored in particle number 1. And then we have a heavier object over here of greater mass m2, so I'm drawing it as a larger blob here, moving, say, at a slower velocity. Okay, so this is v2 initial, and so this is going to be a heavy, slow particle, slow-moving particle. Okay, and so remember the idea that you can have a massive object moving slowly that can have the same momentum as a small object moving quickly. Okay, and so that's roughly speaking, the magnitude of the momentum of these two objects is roughly the same. And I'm just doing that so that when I draw the pictures over here, it'll be easier to draw. Okay, so this is what happens initially. Okay, so there's some interaction force like this happening between them, and then so they repel each other, and then this faster moving one whips over to over here. And so sometime later, it has a velocity v2 final here, and the same mass, v1 final, and the same mass m1, and this guy over here is lumbering along a little more slowly, and so at the end, at the t final time, it's say like this. So this is v2 final. Okay, so when you're talking about momenta, there's always like lots of subscripts: particle 1, particle 2, initial, final, x, y, z component, and so on and so forth. So get used to lots of subscripts. Okay, so great. So we got that, and then so the idea is we've got we're saying that P total final minus P total initial is equal to 0, which means that P total initial equals P total final. Okay, and so let's work these out sort of graphically. So P total initial, what would that be? So initially we have particles coming in like this. So so P total initial would be the momentum or the quantity of motion for this object, which is mass m1 times v1 initial, which is a vector in that direction. And let's sort of like draw it like that. It's something like that. And then we add to that, so remember that momentum is a vector quantity. Okay, so we're going to add the momentum associated with this object at this instant of time with the momentum associated with this object at this instant of time. And it's the mass-weighted velocity, mass m2 times the velocity 2 initially. So it's going to be a vector in that direction. And suppose that m2 is big enough so that it's roughly the same magnitude. So plus something like this. And the tilt angle is a little bit less. So it's maybe something like that. Okay, so that's P1 initial. This is P2 initial. And so initially the total momentum we add these guys up. So we add these vectors tip to tail. And so we take this vector. I should have drawn these a little bit shorter. I'm going to run out of room here. Okay, so it looks like that. So we're going to take P1, and it's this vector. And we add to that P2 initial. That's this vector over here, and we get this vector. Okay, so this vector, I'll draw it a little bit bolder. Okay, this is the initial momentum in the system. So this is P total initial. We have that P total initial. So there's some momentum, there's some quantity of motion like this, and some quantity of motion like this. When you add them together, you get some net quantity of motion like that. Okay. And then P total final in this picture. So P total final, what is that? Well, after the interaction, whatever that interaction was, we calculate the individual momenta will have changed, but the sum of those momenta will not have changed. And so how does that just look graphically? Well, the momentum, the quantity of motion of particle number 1 after the interaction is in that direction, is in the direction of the velocity. And so it's maybe a vector that looks like that. And again, we'll make these a little bit shorter. And then we want to add to that the momentum of object number 2 after the interaction, okay, or at this later time t final. Okay, and so it's going to be a quantity of motion, a momentum in that direction. And so whatever, something like about like that. And so then if we add these two up, we take this vector over here, that vector, and we add to it that vector, and we get this vector. And I'll make it a little bit bolder. Okay, so this is P total initial, this is P total final. These two vectors here are the same. So individually, P1 and P2 have individually changed, but their sum never changes at any instant of time throughout this entire interaction. The sum of both momenta is always the same. Okay, very good. So the second way to think about this is in terms of momentum transfer. Okay, so so let's see here. So for an interacting system, so this was for an isolated system of, say, 2 particles. Now we're going to think of an interacting system. We're going to take this system as the system of interest, the system on the right, system number 2, and we're going to think just about that system. We're going to ignore that system, and we're going to ask, well, sure, P1 started off like, P2 started like this, it ended like this. That's because there was a transfer of momentum from this thing to this thing. Okay, and so that's how we're going to think about it. So for an interacting system as opposed to isolated, so for an interacting system, so we're thinking about system number 2 interacting with system number 1. So going back to our picture like that, the kind of thing we're thinking about is, here is system number 2. Excuse me. That's the system that we're interested in. And the particle is doing this in that system. Excuse me. Okay, and then is interacting with system number 1. Okay, and the momentum in system number 2 changes because there was some momentum transferred from 1 to 2. Okay, and so that's what we're going to be talking about. And that's this this transfer momentum I. Okay, called the impulse, actually. You might recognize that symbol. Okay, so the idea is during a very small interval of time dt, so the particles are just going to move, say, from here to here and from here to here. So during an infinitesimal time interval, we're going to look at how much the momentum in particle number 2 changes. Okay, so in an infinitesimal amount of time dt, in the calculus sense of dt. Okay, so in a time dt, we have the change in the momentum of particle number 2, that's dp2. So you know that the differential, if you know a little bit about calculus, the differential of a function of t, df, is df dt times dt. Okay, so it's the same thing with vectors, vector functions. Okay, so this is the same as dp2 dt times dt. Okay, so the change in the momentum of particle number 2 will be proportional to the small interval of time, and the proportionality is dp2 dt. So, but what is that? Well, we know that p2 is, p is a mass-weighted velocity. It's m2 times v2. Okay, and if m2 is constant, as we're assuming, the masses are constant, you can pull that out. And so dp2 dt is the same as m2 times dv2 dt. Okay, times dt. Okay. However, dv dt, what's that? The time derivative of the velocity is the acceleration. So that's m2 times the acceleration of particle 2 at that instant of time, times dt. And then finally, we know that m mass times acceleration, well, that's the force. Okay. So particle number 2 has mass, inertial mass m2, resistance to change in motion, and has acceleration a2. Well, that's because there's a force. F2 the force on 2 due to particle number 1. So the force on particle number 2 due to some interaction across this imaginary boundary here, okay, acting on particle number 2. So that's the force on 2 due to 1 times dt. Okay, great. And then what we do is, this is the change in an infinitesimal change in the momentum, say from this to this. So an infinitesimal change is during a time dt is produced by a force, the force F21 acting through a time t. So what changes momentum is force acting over time. Just like what changes energy is force acting through displacement, what changes momentum is force acting over time. Okay, we will revisit that in a lot more detail later. Okay, so that's during an infinitesimal time. During a finite time, delta t, say from this initial time when the particles are very, very far apart and their interaction forces are very small, and so they are basically moving in straight lines. Momentum, each individual momentum is constant. Then they start interacting, and as they interact, there's momentum transferred from here to here. And then after the interaction, when they're far distance apart, the interaction forces are small, and the particles are now moving in straight lines, but with different constant momentum. Okay, and so that's the kind of situation we think about when we think about a finite interval of time. It's before and after some complicated interaction. Okay, so then all we do is, if this is true for all infinitesimal instants of time, well, then we just integrate. Okay, so we integrate the left-hand side, dp2 of t. Actually, I'll just say dp2, because the integration variable is in fact p2. So we're going to integrate this from p2 initial to p2 final. Hope that this writing isn't getting too small. Anyways, you could listen to the words. Okay, so we're integrating p2, dp2, and so we integrate the left-hand side, well then we integrate the right-hand side. Integration just means sum. Okay, so we sum f21 and then the instant of time t, dt, we're into the integration of variables t, we're integrating from t initial to t final. So t initial is here, and then it whips through like this, has an interaction, and then t final is at a later time. Okay, so this this sum, this integral of a force over time, is given a special name, and that special name, a special symbol, I, and the name for that symbol is impulse. Okay, so we say that a force acting over time represents an impulse, and it is what causes, it is the amount of momentum that's being transferred. Okay, very much like work is energy transfer, impulse is momentum transfer. Okay, so this is equal to momentum transferred. Now we're talking about transfer mechanisms. Transferred from system number 1 to system number 2, from 1 to 2. That's this guy, this vector. I is moving from system number 1 to system number 2. It's transferred from 1 to 2. Okay? And so then when we integrate this, the integral of dp just means add up all the infinitesimal changes in the momentum, p2, and so what you get is the finite change in momentum, which is delta. So this left-hand side, the integral of dp2 is delta p2, okay, which by definition is p2, the momentum of particle number 2 final, minus the momentum of particle 2 initial. So that vector minus that vector. Okay, so let's do this graphically. So p2 final, So in this picture over here, this is P2 final is this guy over here. So that was this vector here. Okay, so we're just going to take these same vectors, but instead of adding them, we're going to, instead of adding this to get that, and this to this to get that, we're going to take this minus this and this minus this. Okay, so we're subtracting. Okay, so P2 final was this guy. Yeah, P2 final is that guy. And then we subtract now. We're not adding, we're subtracting. We're taking the difference between P2 initial. So P2 initial was this guy over here. So let's write that guy down. And so what we're doing is we're subtracting those two vectors. Well, that's the same thing as taking the first vector, P2 final, and adding the negative of P2 initial. So that means adding this vector. And so then what we get is this vector, which I'll make bold over here. We get this vector. So that vector is called I. And that is the momentum that was transferred from system number 1 to system number 2. So remember, we're focusing our attention mainly on system number 2, and we're saying, hey, the momentum of system number 2 changed. How is that possible? Because momentum is conserved. If it's isolated, it can't change. It's not isolated, it's interacting. And so system number 2 is open to the environment. And so then some momentum flowed from some other system to system number 2, changing its momentum. Okay, so here we're talking about transfer of momentum. Okay, so that's that. And then similarly, we can play exactly the same game, just reverse. Instead of talking about system number 2, we could talk about system number 1. So in the same way that we have the integral of dp2 is the integral of f21 dt, we could do the exact same analysis on particle number 1 here, and we would get this. We would say the integral, it's just this thing that we're writing down, but for particle number 1. It'll say dp1 from p1 initial to p1 final is equal to the integral, instead of the force on 2 due to 1, it'll be the force on 1 due to 2 at any instant of time, integrated over time from t initial to t final. So we're writing the same thing down over here. But you look and you say, but just a minute, F12, if the interaction that we're talking about satisfies Newton's third law, then F12 is negative F21. So F12 there, we replace that with a negative F21. Okay, and then we look, but wait a minute. Put that negative sign up here. Okay, but wait a minute. The integral of F21, over time, we called the impulse I. So we have the negative of that. So this is negative I. So this is equal to negative I. This equals negative the impulse I. Okay, and so this is this is the momentum transferred. We're talking about the change in momentum P1. Well, for momentum P1 to be to change, there has to be a transfer of momentum from 2 to 1. Okay, and so the transfer from 2 to 1 is minus I. So this is the momentum transferred, not from 1 to 2, but from 2 to 1. Okay, just the opposite. Okay, and so then we say, well, what is the change in the momentum P1, sorry. So P1 used to be a momentum, a quantity of motion in that direction with some magnitude. It changed to a quantity of motion in that direction with some magnitude. What was the change? So delta P1, the finite change, that means P1 final, that vector, minus P1 initial, that vector. What is that? So let's do this graphically. So again, instead of adding the initials to get the total initial and adding the finals to get the total final, what we're doing is we're taking the difference of final and initial for 2 and final and initial for 1. Okay, so P1 final, what was that? This is final, this is P1 final, was that vector. Okay, so that looks like that. And then we want to subtract P1 initial. So this was P1 initial, so we're subtracting this vector. like that. Okay, so let's just do this graphically. So that means you take this vector to start with, and you subtract that vector, means you add the negative of that vector. So you add that vector. So that vector plus the negative of that one is this vector. So I'll make it bold again, and it points that way. And so this is, of course, negative I. Okay, so the transfer, the change in momentum P2, we just did it graphically, is the vector I. So there was an amount of momentum I, that vector, transferred from system 1 to system number 2, so that changed the momentum of system number 2 by that amount, that vector. And at the same time, when system number 1 lost an amount of momentum I, then, when system number 2 gained the momentum I, then system number 1 lost the momentum I. The change in the momentum of system number 1 is minus I. Okay, that's this guy. Okay, so system number 2 changed by that, and system number 1, its momentum changed by that, so that the momentum in total doesn't change. Okay, my battery just died there on my camera. So let me just say, the key thing that I wanted to say is that we're talking about transfer of momentum from system 1 to system number 2. And of course, if there's a transfer of momentum from system number 1 to system number 2 of an amount equal to I, then there must also be a transfer of momentum from 2 back to 1 of an amount minus I, so that the total momentum in an isolated system doesn't change. But really, when we're talking about transfer, we're talking about from 1 to 2. We're really sort of ignoring 1. And how did the momentum in number 2 change? Well, there was some transfer. So let me get rid of anything to do with subsystem number 1, because it's exactly the same, just with a minus sign. And let me make a little bit of room here so that I can write down sort of the key kind of summary point here. And what's the key takeaway here when we talk about transfer of momentum? Well, so the key summary point here is an analogy between momentum transfer and energy transfer. So we know that when we're talking about energy transfer, we're talking about force acting through displacement. So I'll write down two statements here, and we'll compare them. So a force acting over displacement transfers energy. Okay, and we think of that as, well, work, the work done. Work is an energy transfer mechanism. Okay, you can transfer energy from one system to another by applying a force on that system. The force vector dot product with the displacement integrated over the trajectory, so a force acting through a displacement. What does that force acting through displacement? I push on a shopping cart with a force, a certain force over a certain distance, and that will represent a change in the kinetic energy. So that's the work done, an energy transfer mechanism. Okay, work done. Well, now, if we look at this, I sort of want to emphasize this point here, that, that a force acting over time transfers momentum. Force acting over displacement transfers energy. Force acting over time transfers momentum. So let's write that sentence down formally. So a force acting over time transfers not energy but momentum. Okay, and so the amount of momentum transferred, well, what do? You take the force that's acting at any instant of time and you multiply by the time interval dt. So in a small interval of time, the amount of momentum transferred is just f dt. And then if you integrate over time, maybe force is a complicated function of time, you integrate that over time, and that will give you the total amount of momentum transferred to that system. And it's a vector quantity. Okay, so if I take a shopping cart and, if I take a shopping cart and I apply a force for a short amount of time, I will change the momentum a little bit. If I apply that same force for a long amount of time, then I will transfer more momentum to the system. So a force integrated over time is what transfers momentum. Now I want you to notice something very important here, and that's the in these two definitions here, or in these two statements here, the difference is sort of displacement, which is space, and time, okay, and energy and momentum. Okay, and so it turns out that when Einstein unified the time dimension with the three space dimensions to get a four-dimensional space-time, he also at the same time unified energy and momentum into a four-dimensional momentum. Okay, so we're used to three-dimensional space and three-dimensional momentum, mass times velocity. But if you add a fourth dimension, time, you have a four-dimensional space-time. And so vectors don't have three components, they have four components. The three of the components are the spatial components of momentum, like mass times velocity, v, x, y, and z components. But now there's a fourth component to the momentum, fourth component to the four-dimensional momentum, which is the time component of momentum. And the time component of momentum in special relativity, you'll learn, is just the energy divided by c to get the dimensions right. Okay, and so when Einstein unified space and time into a four-dimensional space-time, we now talk about a four-dimensional momentum that objects have. Cars have, wind has, and so on, things moving around, light has, and so on. It's all four-dimensional momentum. Three spatial components, the momentum we're familiar with, and the fourth component, which is time. And then so the conservation law, we have conservation of energy, right? Energy is a conserved quantity. Well, momentum is also a conserved quantity, the three spatial components of momentum. So they can be combined together and unified under a single heading, which is conservation of four-dimensional momentum in our four-dimensional space-time that we live in. Okay, and so really this statement of work as force acting through displacement, energy transfer, and impulse as momentum transfer, force acting over time, those are just space and time duals of each other. Okay, and so you can see that energy and momentum are intimately connected to each other. So they're just different components of a four-dimensional conserved quantity, which is the energy momentum four vector. Okay. So very good. And I just want to sort of emphasize again, just before we leave this section here, that the meaning of momentum, really fundamentally, you can define momentum as mass times velocity. Okay, that's all great, and it is a conserved quantity. It's super important in physics. It allows you to solve very complicated problems without knowing anything about the details of the interaction. Okay, very, very powerful. But the real meaning of it is that momentum is directly a measure of the rate of flow of energy. Whenever you have energy in motion, like cars in motion, baseballs in motion, so a lot of rest mass energy moving around, okay, so there's momentum involved. Anytime you have momentum, there's energy flow. Okay, so the two are intimately intertwined. Okay, and so I also want to say, so this idea that a force acting over displacement transfers energy, right? So I've got an airplane which is flying around, and if I look at just one of the forces that are acting on it, say the force of thrust, well, that force of thrust acting over that displacement of the airplane, well, that is a component that adds energy to the system. That's one of the things which changes the kinetic energy of the airplane. But if you add up all of the forces, the work done by all of the forces acting on the airplane, like the net work done by the forces acting on the airplane, or the work done by the net force on that airplane, then you get the change in the kinetic energy of that airplane. Okay, so that's a very, very powerful principle called the work kinetic energy theorem, which we talked about. Well, similarly here, there's a very powerful principle. Sure, I can have one force acting, which is the thrust force acting. That thrust force acting over time will change the momentum of the airplane. But there are other thrust forces acting, which can change the momentum. Okay, and so if you add up all of the forces acting, the net force, and look at the momentum transferred by the net force, well, then you get, the change in the total momentum of the airplane. And so that is, like you have the work change in the kinetic energy theorem, you're going to have the impulse change work kinetic energy the work change in kinetic energy theorem, and the impulse change in momentum theorem, which we will talk about.